Hello, my name is Jameson Ebert, and I'm a PhD student at Texas A&M University in College Station, Texas. The title of this paper is Stochastic Binning, Encoded Demixing for Unsourced Random Access. This paper was written by myself, Dr. Vamsi Amalladinne, Dr. Stefano Rini, Dr. Jean-François Chamberland, and Dr. Krishna Narayanan. Dr. Amalladinne, Dr. Chamberlain, and Dr. Narayanan, and myself are with the Department of Electrical and Computer Engineering at Texas A&M University, while Dr. Rini is with the Department of Electrical and Computer Engineering at National Yangming Chiaotong University. This work was supported in part by the NSF, by Qualcomm Technologies, and by the Taiwanese Ministry of Science and Technology. So let's get started. The conceptual starting point of this work is coded compressed sensing, first proposed by Amalladinne et al. In 2017. In coded compressed sensing, each user's B-bit message is transformed in a length 2 to the B one sparse index vector, where the single unitary entry represents the message to be transmitted by the user. This length 2 to the B vector is then compressed, transmitted across the channel, and recovered using standard compressed sensing techniques. However, for even moderate values of B, this problem quickly becomes computationally intractable. To deal with the exceedingly large dimension of this problem, coded compressed sensing leverages a divide and conquer approach, whereby the original message is divided into sections. Each of these sections are linked together with an outer graph-based code, and each encoded section is compressed, transmitted, and recovered individually. After recovering the various sections, they are linked back together by decoding the outer code. Over the past several years, several variants of coded compressed sensing have emerged. We will focus on a specific variant called CCS-AMP, which was also proposed by Amalladinne et al. So CCS-AMP encoding proceeds as follows. Each user's information message will be broken down into fragments of length V. Each of these fragments can be viewed as an element over the Galois field of order 2 to the V and encoded using the rate-R LDPC code. After being encoded using this LDPC code, each fragment is converted into a one sparse index vector of length 2 to the V, where the single unitary entry is at the index given by that fragment's message under radix 10. After each fragment has been converted to its sparse representation, the L encoded sections are jointly compressed using a fast Walsh-Hadamard transform-based sensing matrix. The K active users then simultaneously transmit their compressed encoded messages as facilitated by a beacon. The receiver is then tasked with producing an unordered list of the K transmitted messages. It begins by performing compressed sensing support recovery on each of the L sections, using approximate message passing or AMP. Within the AMP denoiser, one round of belief propagation is run on the outer LDPC factor graph. This ensures that AMP converges to a parity-consistent solution. After AMP has converged, the decoder has L K-sparse vectors, which can be interpreted as L lists of K message fragments. To recover a transmitted message, the message fragments need to be connected across sections. This is accomplished by running the belief propagation-based LDPC decoder. At this point, decoding has been completed. CCS-AMP has shown to perform exceptionally well. However, it does have a very big weakness, and that is that multiple users reside on a single factor graph. This renders the application of belief propagation very difficult, as belief propagation must balance multiple parity-consistent code words on the same factor graph. Historically, a modified version of belief propagation has been used with success. However, the purpose of this paper is to discover ways to reduce the number of users on a single factor graph, with the hypothesis that this will improve per user probability of error. Our proposed solution to this problem relies on some results recently published by Amalladinne et al. In ISIT 2021, wherein a connection is drawn between coded compressed sensing and coded demixing. This connection allows multiple classes of heterogeneous users to simultaneously communicate with a central base station within the CCS framework. To do this, each class of users employs its own sensing matrix and outer factor graph, and the set of sensing matrices is specifically designed such that the sensing matrices exhibit very low cross-coherence. The encoding process proceeds as follows. Each class uses its own sensing matrix and factor graph for standard CCS encoding. Then each class of users simultaneously transmits its signal over the multiple access channel. Because the sensing matrices are nearly incoherent, ideas from the field of coded demixing may be used to separate the transmitted signals as the support is recovered. After the support has been recovered for each class, message disambiguation may proceed in a traditional CCS manner for each bin individually. This process may be done efficiently using an AMP-based algorithm that was proposed by Amalladinne et al. In their ISIT 2021. With these results in mind, we are ready to present the main idea of this paper, which is, to reduce the number of users present on a single factor graph, we propose to stochastically group users into bins, where each bin uses its own sensing matrix and factor graph for CCS encoding, and then to employ a coded demixing decoder to recover the messages transmitted by each user across bins. Our proposed scheme differs from existing CCS schemes and from the coded demixing scheme of Amalladinne et al. In several important ways, which we seek to highlight briefly at this time. The first important difference lies in the fact that users are randomly assigned to groups or bins. We emphasize that this process must be random, as there is no way to know a priori which devices will be active at any given point in time within the unsourced random access framework. The stochastic binning of users proceeds as follows. Each user's information message is broken into two parts. The first W0 bits are used to determine the user's bin, and the remaining W bits are outer encoded, compressed, and transmitted across the channel for coded demixing recovery. We point out that one consequence of this scheme is that an additional 2 or 3 bits of information are conveyed by the users to the base station with each transmission based on which bin they select. However, this gain is small and is neglected with all results presented in this paper. Another difference lies in the fact that the number of users contained within each bin is unknown to the receiver. As is conventional within unsourced random access, the total number of active users is known. However, the distribution of users among bins is unknown, and thus it must be estimated by the receiver. Since estimating the number of users per bin during the decoding process turns out to be very difficult, a bin distribution sequence is first transmitted before transmitting the information message, from which the distribution of users among bins is inferred. This process proceeds as follows. Each user is first assigned a bin based on the first W0 bits of its information message. Then, each user simultaneously transmits a one-sparse index vector indicating the assigned bin, where the single unitary entry is at the index corresponding to the assigned bin number. After the base station receives k superimposed index vectors, the receiver employs a standard LMMSE estimator to jointly estimate the number of users contained within each bin. These estimates are crucial for the accurate and efficient recovery of the transmitted messages. We emphasize that under the URA framework, the total energy used by each device is strictly upper limited. Thus, to facilitate a fair comparison with other schemes, the energy used for the bin identification process must be subtracted from the total energy budget. Empirical results showed that using 0.2% of the total energy for bin distribution estimation results in good per-user probability of error. After the receiver estimates the number of users per bin, each user encodes and transmits its message over the multiple access channel in traditional CCS AMP fashion. That is, each user's information is first divided into sections and encoded using its assigned bin's outer factor graph. We note that while each bin employs a separate factor graph, all factor graphs are identical. After the sections of the information message have been linked together, they are jointly compressed using a fast Walsh-Hadamard transform-based sensing matrix. Each user then transmits its compressed message simultaneously over n channel uses. This operation can be viewed in many ways. One particularly instructive way to view this operation is to imagine a very wide matrix encoding a very tall vector, where the wide matrix is composed of the individual sensing matrices stacked together horizontally, and the tall vector is composed of each bin's signal stacked together vertically. Under this interpretation, it becomes clear that the decoding process is amenable to approximate message passing, or AMP. The AMP algorithm iterates between the computation of a state update and the computation of a residual error, as shown on this slide. The first equation computes the residual error incurred by the current state estimate, enhanced with an Onsager correction term, which is characteristic of AMP. The second equation computes an effective observation based on the residual error, and the third equation computes the updated state based on a denoised version of the effective observation. The denoiser used within this algorithm is a modified version of the posterior mean estimate denoiser first proposed by Fengler, Jung, and Kerr. The PME denoiser operates on each bin's state separately. Priors are computed by running one round of belief propagation on the selected bin's outer factor graph. This dynamic sharing of information between the inner AMP decoder and the outer LDPC decoder ensures that AMP converges to a parity-consistent solution. While the wide matrix and tall vector interpretation of this algorithm offers insight into the decoding process, the problem may be broken down such that each state update is performed individually and the residual is computed jointly. This approach is employed by authors in all simulations presented in this presentation. Once AMP has converged, the support of the transmitted messages within each bin is known to the receiver. This enables the receiver to perform message disambiguation, albeit with several key modifications. First, the decoder will run belief propagation within each bin until ki hat plus delta code words have been identified. These potential code words will be stored alongside their respective likelihoods. After the decoder has performed this operation for all bins, the lists of code words will be merged together and sorted in terms of decreasing likelihood. The top K code words from this list are retained and are considered to be the K transmitted code words. As is conventional within unsourced random access, the predominant criterion used to evaluate this scheme is the per-user probability of error, sometimes referred to as PUPE, which is defined to be the average probability that a transmitted message does not appear in the list of estimated messages at the receiver. We ran extensive simulations to compute the per-user probability of error of this scheme under 2, 4, and 8-bin scenarios. This figure summarizes our results. The system parameters used in this plot were inspired by the LoRaWAN specifications. There are K equals 64 total users that transmit over 38,400 channel uses. Each user's message is 128 bits long, excluding the extra bits used for bin assignment. Each point is averaged over 100 trials for statistical accuracy. In this plot, the x-axis represents EB over N0 in dB, and the y-axis represents the per-user probability of error. The black line in this figure represents the performance of CCS-AMP, which is the benchmark that we were aiming to beat. Solid lines represent the performance of the stochastic binning with coded demixing algorithm using real estimates, while the dashed lines show the performance of our algorithm using Gini-aided estimates of the distribution of users across bins. From this plot, it is clear that stochastic binning with coded demixing outperforms CCS-AMP in this regime. For a target PUPE of 5%, Stochastic binning encoded demixing offers a nearly 0.4 dB gain. Furthermore, it appears that increasing the number of users improves the per-user probability of error performance of this scheme in this regime. Before concluding this presentation, a discussion of the side effects of employing multiple bins is warranted. This plot is a plot of the convergence region of AMP for various values of the undersampling ratio delta presented on the x-axis and the sparsity ratio rho presented on the y-axis. Each line in this plot corresponds to a different version of the AMP problem. When the undersampling sparsity ratio of a scheme lies above its corresponding curve, AMP is guaranteed to converge with high probability. When the undersampling sparsity ratio of a scheme lies below its corresponding curve, a phase transition occurs and AMP does not converge. None of the three curves shown in this plot correspond exactly to the scheme presented in this paper, but this plot is included in this presentation nonetheless to provide intuition for the following discussion. We now consider the undersampling ratio delta and the sparsity ratio rho for the stochastic binning encoded demixing scenario. The undersampling ratio delta equals n divided by BL2 to the v, and the sparsity ratio rho equals KL divided by n. Thus, as we increase the number of bins B, the undersampling ratio decreases while the sparsity remains fixed. Graphically, this corresponds to moving the operating point of the algorithm to the left while maintaining a constant y value. Clearly, for high enough values of B, the operating point of the algorithm may fall out of AMP's convergence region. This suggests that there may be an upper bound of how many bins can be employed before decoding fails, but the exact characterization of such a bound remains an open research question. Furthermore, the coded demixing ideas used in this paper rely on the fact that the cross-coherence between various bins' sensing matrices remains very low, and increasing the number of bins may increase the cross-coherence between matrices, further weakening the decoding algorithm. Again, an exact characterization of this phenomenon remains an open question. To conclude, the performance of CCS AMP is limited because belief propagation must decode several users' code words simultaneously on a single factor graph. To mitigate this issue, users may be stochastically grouped into bins, where each bin employs a unique sensing matrix and a separate factor graph for message encoding. Ideas from the field of coded demixing may be applied to coded compressed sensing to separate the signal sent by the various bins at the receiver. This allows for the efficient and effective recovery of all transmitted code words. This scheme uniformly outperforms CCS AMP in the regime considered in this paper. Finally, increasing the number of bins appears to improve the per-user probability of error performance of this scheme up to a point. An exact characterization of the effects of multiple bins remains an open research question. Thank you for attending this presentation. If you have any questions, please feel free to reach out. We'd love to hear from you. Thank you.